This is one of the strangest places on Earth. It's the inside of a vast, sophisticated machine, which is driven by an ancient technology. It's a tanker with a cargo that can power London for about a week. A cargo equivalent to the energy of 55 nuclear bombs.
This huge ship is carrying liquefied natural gas, millions of litres of the stuff. At room temperature, it turns into a highly flammable gas. That's why people want it.
The liquid inside these tankers becomes gas for cooking and heating your home.
Creating the technology to transport it is very complex. Yet these ships owe their existence to some surprising connections.
Kitchen cutlery. The father of evolution.
And there it goes.
The world's first steam engine. World War II fire engines. And air-to-air refueling. Transporting natural gas around the planet is a big business. This supertanker is larger than the Titanic and is designed to carry natural gas all over the globe.
She's a big ship, yeah, so you know everything about her is going to be super scale. But it's only when you get close up do you realise how big.
Admittedly, I'm not the tallest chap you'll meet, but it would make even him feel small. The propeller alone is more than 5 times my height and weighs 48 tons. The whole ship is nearly 300 meters long, about 2.5 football pitches, and it takes a lot of looking after.
Every time she comes into dry dock like this, she's repainted. She is quite big, so it is quite a lot of paint. 12 tons of it gets applied.
I didn't come here simply to feel small. I can do that anywhere. I came here because I want to see how these ships shift huge quantities of gas all around the globe. They have vast tanks, but getting inside them is very tricky. The ships have to be in dry dock, and the tanks have to be completely purged of any trace of their hazardous cargo. This is the inside of one of the tanks, and as far as we know, nobody's ever actually filmed inside one of these before. That seems a shame, because look at it. All you need is one light, one camera. You can make a sci-fi movie and listen to it. That echo is real, analog, not a digital effect. Real sounds bouncing around this cavernous tank. There's room for 34 million litres of liquid gas in here. The equivalent volume of water would allow the average British home to flush the toilet for 1,200 years. And there are 4 of these, each at minus 160 degrees inside. Just another world. It's just crazy. Just like oil, natural gas is a fossil fuel found where ancient organisms decomposed. It can be shifted in pipelines, but they are expensive and impractical for crossing oceans. Instead, engineers had to work out how to transport it by ship. That's a challenge when you remember that natural gas ignites at any air temperature found on Earth. To learn how you transport gas safely, I went to a high-security research facility in northern England. This is a blast-proof chamber, a sort of industrial-scale oven.
Right, well, this device here is a supply of gas up through this tube here. This is an igniter, it'll create a spark, light the gas, and it'll burn. It's quite a lot of gas, a lot more than you're used to at home, but don't worry, this place we're in can take it. This is a specialised blast testing facility. They use it to test industrial safety equipment on a massive scale, so it'll be okay. Nevertheless, I think I'll get out while we light it.
Since someone had left the oven door off, we had to retreat to a safe distance. Cue the spark.
5, 4, 3, 2, 1. Release gas.
That's just a few litres of gas. Imagine a cargo of many millions of litres that could be ignited by the tiniest of sparks. That cargo has the energy equivalent of 55 atomic bombs. Spilling it could be a massive disaster. But there has never been any major accident, and the operators plan to keep it that way. Fortunately, there's a simple solution. Turn the gas into a liquid. As a liquid, it can't catch fire. And what's more, it takes up much less space. If the cargo were in gas form, the tanker would need to be impossibly big.
It would have to be 600 times more voluminous, which would make it 10 times longer than this ship. 2,500 metres, a mile and a half.
To make the gas liquid, you chill it to minus 162 degrees Celsius. That's nearly twice as cold as it ever gets in Antarctica. But it only has to warm a little bit to turn back into highly flammable gas. So the crew are hopeless with their volatile cargo, as I found out when I went on board a fully laden tanker.
As a liquid, it won't explode, nor will it burn. But the operators of LNG carriers can't take any chances with safety. So to avoid even the remotest risk of igniting any gas vapor, electronic devices are not allowed near those tanks. If I want to go forward from here, the bridge at the stern, I can't even wear a microphone. So, it's got to go. There you go.
Neither can I take my telephone, my camera, and certainly not a TV crew beyond the bridge. They take no chances with this precious cargo. If you could hear me, I'd be saying that under my feet is a tank exactly the same as the one I climbed inside earlier. It's one of 4 full of ultra-cold liquid. That's an awful lot of natural gas on these ships. Keeping it as super cold liquid is the first and best line of defense. But what if any of the cargo warmed up and turned back into gas? The consequences would be dire. So there is a second line of defense.
Normally the cargo is the other side of these walls. Tens of millions of litres of it. And remember, that's in liquid form. Expand it into gas ready to use, and it's billions of litres. And if any of the liquid made its way and leaked out and turned back into vapour, well, that could be a big problem. But it doesn't, thanks to a pre-war mail plane.
In the 1930s, Empire flying boats delivered mail and passengers from Britain to Australia in 700-mile hops. They couldn't cross the Atlantic until they were able to take on fuel during flight. Nowadays, we take mid-air refueling for granted. But aviation fuel, just like natural gas, is highly flammable. A single spark when the refueling pipe makes contact and, well, it's kaboom.
What aviators needed was something to stop an explosion if there was a spark. What they needed, in fact, was noxious air. That's the name Daniel Rutherford gave nitrogen when he first isolated it in 1772. There might be lots of nitrogen around in the atmosphere, and there is a lot, but in its pure state, we can't breathe it. Sadly, it took a dead mouse in the container of the stuff to make that particular scientific advance. But the point here is nitrogen is an inert gas. It doesn't react readily with anything at all. And more importantly, it stops fuel combining with oxygen if there's a spark. Ignition is impossible if there's enough nitrogen around. Fires can't breathe nitrogen either. And that's a claim that just needs to be put to the test.
So, time to fire up the industrial oven once again. This time with nitrogen inside it. First, it's sealed to contain the toxic gas safely. Nitrogen on. I get to watch from inside a special canopy to the side. A meter shows how the oxygen level drops as nitrogen replaces the normal air around the igniter. Remember, the theory is that gas won't burn unless there's enough oxygen present. That 10 means there's hardly any oxygen in the chamber. It's now mostly nitrogen.
I know the science, I know the physics, I know this should work, but suddenly I'm strangely nervous. Maybe it's just the drama of the surroundings. Right, if we're ready to do this, let's kill the nitrogen supply. Okay, let's have the spark on then, please. This is the igniter, no gas in there yet, remember. So very soon we'll see the sparks at the top of the funnel. Let's have a look. There they go, that's the spark. Smoke on them, please. Now, the smoke is purely an indicator here, because otherwise we won't be able to see when the gas starts flowing. Right now, no gas going in, you can see the smoke. As soon as the gas starts, it'll pull the smoke up through that funnel.
The chamber is full of nitrogen. The spark is firing.
We can have the gas on then. And at that point, the only thing stopping ignition has to be the nitrogen. There goes the gas. Look at it, you can see where the smoke's coming out the top. That's been pulled through by the gas. That's the same gas we saw burning earlier. And yet with the nitrogen in there, look at that. Nothing. Do you know what? I find that strangely comforting. Science tells you it should work, but there it is working. Look at that. Gas charging in now. The nitrogen quashing it. It can't ignite. It can't burn.
Nitrogen also protects gas tankers and mid-air refueling. A quick squirt of nitrogen down refueling pipes removes any risk of explosion. Thanks to nitrogen, an Empire flying boat made its first transatlantic flight back in 1938. On gas tankers, the potentially poisonous nitrogen is safely sealed inside the gas tank insulation. This thin layer of aluminium, almost foil, is the outermost skin. But obviously if I were to poke my finger through it, it wouldn't go straight into a tank full of tens of millions of litres of liquefied natural gas. On the other side of the aluminium, There's a layer of insulation that's critically to keep the temperature low. Then there's the aluminium tank itself. But that layer of insulation isn't just about temperature. It's porous and it's been steeped in nitrogen. So if there is a problem in the tank, nothing can burn. There's no oxygen. It's inert. In case of a leak, nitrogen stops the volatile cargo reacting with oxygen, and the insulation keeps it in liquid form. The gas is chilled on shore, and the liquid is then piped onto the tanker. But these super cold temperatures pose big engineering challenges. You can't just use standard steel pipes to do the job.
Moving the ultra-cold liquid around the place, off the ship and around the ship on pipes like these, presented a whole new set of problems that could only be resolved by recourse to the engineering might of this, and of this, and even of this. But no, not actual cutlery, obviously. That'd take hours. No, what it's made of.
Stainless steel. 100 years ago, cutlery was made of other metals, silver, say, or plain steel for everyday tableware. But steel rusts, off-putting at dinner, and like many materials, it changes completely when you put it in the deep, deep freeze.
Subantarctic temperatures are a game changer. Suddenly, strong things that you thought you could rely on, like metal, behave differently when you put them in the deep, deep freeze. It's all about ductile to brittle transition temperatures, which is how the properties of things change with temperature. An example, bread. At room temperature, a slice of bread is bendy, flexible, ductile in the jargon. Take the same piece, freeze it, it's harder, but brittle. Wouldn't it be terrible if steel behaved the same way? It does.
Jackie Butterfield, a materials specialist at Seoul, introduced me to a medieval torture device.
This is the sort of equipment that we'd use to test the toughness of a metal.
Right, can I help?
Absolutely.
Oh, good. What'll I do?
First thing you can do is lift this weight up and we'll lock it in position.
Right, thank you. Okay, I always get the nice jobs. Right, so just swing this back, yeah?
Yeah.
Right, it's got a lot of weight.
Just for the record, I'm not being a complete weakling. It is actually quite heavy, about 10 kilograms.
So it's a fitness program?
It is, absolutely.
Okay. Right, so that's... the weight is primed.
Yeah, so what this is going to do, this weight has potential energy.
So that's a measured dose of energy that we can apply to the sample down there.
Absolutely.
It's the same each time because the weight is the same.
Step forward, victim number one. A length of standard steel tube, just like a scaffolding pole.
Triggering test. So this is going to return a specific amount of potential energy transferred into kinetic energy that will be absorbed or not by the sample. Okay, here we go. 3, 2, 1. Woohoo! It's not even dented it.
Despite the full force of the weight slamming into it, at air temperature, the bog standard carbon steel remained undamaged, whilst the energy ricocheted through the frame around it.
So this sample has survived then?
Absolutely.
What are we doing now?
Right, what we need to do now is test some of the carbon steel at the cryogenic temperatures with the liquid nitrogen.
So this is where we introduce our tricky subantarctic temperatures.
Absolutely.
Cue liquid nitrogen, minus 195 degrees Celsius. This will give the steel the same kind of thermal shock as the chilled liquid natural gas going into the tanker.
Thank you, mysterious man with a large large vat of liquid nitrogen. He just follows me around. I've got to be really careful here. Goggles. Just put it in.
Yep.
So, the liquid nitrogen is going to be removing the heat from the steel. For how long do we have to leave that?
Just for about 10 seconds, it should get down to the
What?
to the right temperature.
In 10 seconds?
Yeah.
That liquid nitrogen will have removed that much heat energy from the steel?
Yes, it
That
will.
quickly? No wonder you have to be careful not to spill it on yourself. Right, coming through.
So the liquid nitrogen has dramatically lowered the temperature of the steel, just as the gas cargo would do as it's piped on board the ship.
Right, if we're ready, 3, 2, 1. Bit's broken. Badly. Look at that. It's just shattered. So it's exactly the same sample, same metal. This one barely a scratch. This one, well, ruined. Just shattered. Behaved completely differently.
In a brittle manner.
Brittle, ductile.
Ductile.
Brittle, ductile. Cold.
Clearly then, you wouldn't want to rely on that anywhere really cold, in a liquid gas tanker, for instance. Instead, the tanker engineers needed a material that can withstand super cold temperatures, which brings us back to cutlery of the stainless steel variety. In 1913, British chemist Harry Brearley was looking for a tough metal for gun barrels. He mixed chromium and steel, but it was too soft. However, the reject alloy revealed two unexpected benefits. It didn't rust, which was good for cutlery, and even better for liquid gas tankers. Putting this new stainless steel in the deep freeze doesn't make it brittle.
So, loading it in. Ooh, that's slightly sort of frightening when you do that. Right. Here is frozen sample. 3, 2, 1. That's completely... It's just shrugged it off. So what's actually happening in it that's so different? Why is this fine and that's ruined?
Because of the alloying elements in the stainless steel, it's changed the crystal structure, the way the atoms are arranged in the metal.
So the difference between these two samples is right down at the atomic level.
It is, yes.
And that's where its ability to absorb the energy or be ruined by it stems from, right down at that level.
Simply adding some chromium can make ordinary brittle steel stand up to cryogenic temperatures.
The engineers who built the LNG carriers ensured that not only were the hulls fit for the 7 seas, but that the thousands of meters of intricate pipework, with all their vulnerable bends, joints and tapes, were made of a material that could take it when the going gets cold: stainless steel.
But transporting liquid by ship brings another challenge: stopping it from sloshing. And engineers have 2 liquids to worry about on these tankers. On the way out, they have a cargo of liquid gas, and on the return journey, when it's empty, they carry water as ballast to stabilize the ship. The same problem in 2 different forms.
If a liquid cargo starts to wash around on a ship, it can be a real problem. Basically, when wind or waves rock the ship itself, that can send the liquid sloshing from side to side in the tanks. That motion can build, emphasizing the rocking of the ship itself, and, well, it can be disastrous.
It's called the free surface effect. I set out to discover just how bad it can be. And yeah, given my driving record, I am, well, perhaps more than a little nervous. Only a bit.
Right, what I have here is a van, perfectly ordinary, apart from the massive tank fitted into the back, containing water, a lot of it. Water that's free to slosh about. So what I'm looking to experience is, for myself, firsthand, the free surface effect.
The free surface is literally the area available for a liquid to slosh around freely. And just in case it does affect the van, I'm securely harnessed inside a roll cage. First, I took it slowly, to ensure just a little bit of sloshing.
As I turn into the corner, obviously the water wants to stay where it is and sloshes off to the right. Ooh, it does, yes, it is sort of affecting the way it feels. If I go this way and then this way, it doesn't feel. Ooh, yeah, it's sloshy. I can feel it suddenly jerk the vehicle in a direction other than the one in which I want it to go. I don't know whether it's me driving or the tank of water. That's a strange feeling.
Time to step on it and imagine our ship and its liquid cargo rolling through stormy seas. Well, step on it as much as I can in a van.
Yeah, a lot of water going over. It's very unpleasant. Didn't go as well as it might have done.
As I corner, the momentum of the slosh capsizes my little van.
Yeah, that is the free surface effect. As it turns out, it's deeply uncomfortable.
Scale my tumble up to a whole ship and disaster ensues. In 1987, the free surface effect capsized the Herald of Free Enterprise ferry when water gushed in through doors that had accidentally remained open, and almost 200 people died. Liquid natural gas tankers have a surprising solution to this. To surface area, the gas tanks are spherical, like great big balls. There's less room for sloshing, as long as the tank is full or nearly empty.
These tankers fill up with cargo, 98%. Set off, make a long journey, get there, and discharge it, or nearly all of it, keeping back just enough to use as fuel for the journey home. So the tank, in normal circumstances, is either almost entirely full or almost entirely empty. No sloshing.
Empty of cargo, the tanker would ride high in the sea. To lower it, water is pumped into ballast compartments in the hull beneath the gas tanks. Space doesn't allow these compartments to be spherical, so preventing sloshing here calls for a different solution. Rewind to World War II. Bombing raids kept British firefighters busy. They used a tanker lorry carrying almost 4,000 litres of water. The free surface effect made it dangerous to drive. By contrast, modern fire engines hurtle around without overturning. And that is thanks to baffles, not as in confusion, but load dividers. These are physical barriers, first introduced in the 1880s to stop oil tankers capsizing.
Obviously, what led to my slight incident there was the free surface effect, allowing the water to slosh from side to side, and it brought the whole van over. So the key ones here in my baffles are these longitudinal ones that stop the water going from side to side. Apparently this works. Find out. So far, all seems okay.
And just as they keep the van stable, baffles also protect tankers from capsizing. Dividers in those ballast compartments under the gas tanks stop the water from sloshing around. No free surface effect. Surprisingly, they don't use baffles in the gas tanks. One reason is because friction could heat up the cargo, turning it back into gas. And you wouldn't want that. Empty or full, these ships are stable. But propelling a full tanker is more than a little challenging. Fully laden, This tanker weighs 113,000 tons. Once underway, it takes an hour to bring it to a complete standstill. But how do you get it going in the first place? You might expect a modern vessel to be driven by a complicated computer system with some very fancy mechanisms. Well, you'd be right about the computers, but the mechanisms are a different matter.
At the heart of this vast tanker, there is, not surprisingly, a vast engine. It's immensely powerful, making 30,000 horsepower, in fact, to drive the ship across the seas round the world. It's very clever, it's very high-tech, but inside, it's based on a principle that was first used hundreds of years ago.
Tens of hundreds, in fact.
Meet the 2,000-year-old Aeoli pile, or as it's more commonly known, Hero's engine, after the Greek scientist who invented it. Here's how it works. In the base here is a reservoir of water. What I'm going to do is heat that water up, thus. When you heat the water, it turns to steam. This bit goes on top, so the steam rises up here. And now, the only way out for the steam is through tiny, tiny holes in the ends of these nozzles here. Then it all gets a bit Newtonian, because when the steam comes out that way, it exerts an equal and opposite reaction, a push that way, and sets the top spinning. All we've got to do now is wait for it to build up pressure. There wasn't much to be doing in those days, obviously, so waiting for things was great. Do some philosophy while we wait, perhaps.
You might think this spinning pot is simply a toy. But no, this same principle was used by the ancient Greeks in a machine to open temple doors. Fast forward a couple of thousand years and steam transforms the world, powering industry and transport. And then steam engines went the way of top hats, and now we think of them as yesterday's machines. But in a safely remote, muddy field, I set out to learn what the engineers of liquid gas tankers know very well. Steam is powerful. You just need to put it under pressure. The more, the better. I've brought steam engine specialist Richard Gibbo, along to demonstrate steam's true potential, or with a bomb. We're going to put water in this super strong container buried in the mud. Steam from the traction engine will heat the water. Normally, it would boil, turn into gas, and escape, just as it does from your kettle. But that shiny lid prevents the water from turning to steam because it can't expand. There isn't room. Instead, the pressure inside will simply get higher and higher until it explodes.
So this whole setup, Richard, is all about the power of steam. Now, I'll be honest, I think steam, I mean, look at that sweet old thing, it's from the past, and you've got this little pot in the ground here and a pipe. Is steam that powerful?
Yes, it is. And there's a massive amount of energy locked up in water that is changing to steam. And that's what this experiment's going to demonstrate.
Richard, what's the shed for?
The shed's just to demonstrate that steam has a lot of force, power, energy.
So you're going to break this shed, I'm guessing?
Hope so.
Even well above its normal boiling point, the water won't turn to steam until the pressure is released when the lid bursts off. Then it will expand instantaneously, creating an explosion. First, though, the sacrificial shed.
Nobody walk on the big disc.
How many crack engineers does it take to move a garden shed? Quite a lot, it seems. Then even then, they managed to break it.
I don't know, has anybody seen a steam bomb?
Well, we'd never done this before. It's new.
It's going well, this.
With the soon-to-be ex-shed in place, we fired up the boilers and Richard opened the valve to pump steam into our underground kettle.
Okay. Slightly nearer.
As steam bomb is ticking, and now all we can do is wait. As the metal kettle gets hotter, you can see the puddles around it boil and turn into steam. But the water inside, although it's well above boiling point, can't turn into steam until the lid blows off.
Okay. It's moving. Yes, it's moving.
The pressure gauge needle slowly ticked up. Gibbo expected it to blow at around 5.5 bar, which is 5.5 times atmospheric pressure. The boiling, muddy puddles make the shed steam like a Finnish sauna. The kettle lid starts to buckle under the mounting pressure.
I think we should be at the bridge.
We retreated.
6.5.
And now we really are into unknown territory.
Come up to 7. Properly dangerous now.
Any more, and we'll be close to running out of steam. The traction engine can only handle 10 bar, and if that lets go...
That went.
Brilliant. What did that reach?
7.5 bar.
That's-
And the shed is no more.
The simple power of boiling water had given our shed an extreme steam clean and completely obliterated it. The vessel itself was fine, while the lid had been blown off.
There's the discs.
Yeah.
And you can't really see, but the vessel is empty and dry.
Every single bit of water turned
Yes.
instantly to steam and therefore expanded massively. So it's just force. Sorry about your shed. You've ruined it. Yeah. Yeah, steam is perhaps more powerful than I thought.
And it's that same steam power that drives giant liquid gas carriers through the world's oceans. As you might expect, everything about these tankers puts our mini steam bomb to shame.
This is also a pressure vessel, like the one I used to clean my shed, only it is a bit bigger. And there are 2 of them. And these are generating high-pressure steam all day, every day. So although in some ways this whole engine room looks a bit inert, a bit inactive, it's actually generating and containing incredible quantities of energy and power all the time.
Compared to 140 degrees in our pressure kettle in the shed, the steam here is at 510 degrees, and the pressure is 8 times higher. Mark Hodgson manages a liquid gas tanker fleet. He puts the power produced by those 2 massive containers into perspective.
They're just boilers making steam, and together they produce 110 tons an hour. That is equivalent to about an Olympic-sized swimming pool is processed by these units every day. And that steam pressure and temperature is delivered downstairs to the turbine.
All right, so steam made here in big boilers. Steam goes downstairs to the turbine, and this is where Hero's engine comes in.
So the same principle that turned Hero's engine powers these monster tankers. It turns the propeller. It also provides all of the electricity for every single appliance on board, right down to the crew's TV. On these ships, the secret of harnessing power from steam lies in their turbines. Mark shows me the amazingly simple machine that generates the ship's electricity. Its lid was off, and you could see the hundreds of turbine blades that the steam physically turns.
Okay, so steam comes in that end,
Yes.
and then what?
As the steam is injected at each stage, this is where you get the rotational forces applied to the rotor itself.
This is where it starts to turn, the whole thing. So there's an immense amount of force going through here, which rather explains the enormous stud bolts here, because the pressure contained within this when it's up and running is huge.
It's a large casing, has to contain 60 bar steam.
There is such a thing as a beautiful simplicity, and this incredibly clever device has one moving part. The engine that drives this entire ship has one moving part. This, turned by steam. You wouldn't want to catch your tie in it, would you?
Not really.
This turbine is powerful, but the one that drives the ship delivers 7.5 times more power.
The steam made in the boilers drives the turbine over there behind me. That comes through to the gearbox, and from the gearbox is transferred to the propeller shaft there. And then out there at the stern of the ship, the propeller shaft turns the propeller itself. At that point, it bites into the water and shoves forward with incredible force.
These tankers are designed to be super efficient. They cannibalize their own cargo to produce steam. And for the 25 tons of water they consume every day, they turn to the surrounding ocean. But salt water is horribly corrosive, and the crew just refuse to drink it, softies. So all the seawater is boiled and evaporated to remove the salt. And once again, it's steam that does the work. But to make it even more efficient calls for a principle noted by the father of evolution, naturalist Charles Darwin. Investigating wildlife in the Andes Mountains, Darwin noticed something that plagues all mountaineers who try to boil potatoes. They take ages to cook. Darwin put it down to altitude, and he was right. We learn that water boils at 100 degrees C. But as Darwin noticed, the boiling point varies if you're up a mountain. The potatoes were taking longer to cook because at altitude, air pressure is lower, so water boils at a lower temperature. The boiling water just wasn't hot, and you can't cook potatoes in cold water. You can even boil water without heating it at all, if you reduce atmospheric pressure enough.
Right, switch the pump on. That is sucking the air out of there. That's lowering the pressure. This is to prove that water will boil at a lower temperature at lower pressure. So, my marshmallow man is to prove... See? That's a vacuum in there.
As you can see, marshmallows expand in low pressure. Useful to know.
Yeah, it's grisly, sorry. But the point here is not to prove what happens to marshmallow men in low pressure, albeit quite funny. It's what happens to water. Actually, this is just like taking it up to high altitude where the pressure's lower. But obviously this is easier.
In fact, the pressure in the jar is the equivalent of being at 85,000 feet, almost 3 times the height of Mount Everest.
I think I can see some bubbles at the bottom. Remember, I'm introducing no heat here. It's just a room temperature, and this room is at a very low temperature. Oh dear. And there it goes. Now, that's not just splashing of it, that water is boiling. And that's not because I've introduced any more heat to it, that's just because I've lowered the pressure. Right, I shall now prove that it really is just at room temperature. Air flooding back in, pressure coming back up. Sorry, Marshmallow Man, bad day. The point being, room temperature. In fact, really very cold, but boiling away happily. I mean, you wouldn't want to make a cup of tea with it, but point, I think, is proved.
So, boiling doesn't mean water reaches 100 degrees. It simply means it turns from liquid to gas, which it does at different temperatures according to pressure. And on this ship, just as I did in my vacuum flask, they boil water at a low temperature by reducing the pressure. Once again, they harness steam. But they reverse the high pressure process when you make water expand quickly into steam. You make low pressure by going back the other way, condensing steam rapidly into water.
You need something called a flash condenser, and I'm going to build my own. 1 barrel to start off with, so that goes...
On board, they use leftover steam from the engines, but I need to rustle up my own. So, first, add a little water. Apply heat.
Gas on.
Wait, and wait, and wait. And hey presto.
Right, finally, we've got steam. So, very quickly, I've got to remove the heat and seal it. Quickly as I can. So, heat comes out, lid goes on. I've got to really seal it because it's important no air can get in. That's sealed. Right, it's full of steam. What I'm going to do now is condense that steam back into water quickly. Here's the way. Right.
Cold water will flash condense the steam, reducing the pressure.
You can hear it creaking and groaning. As that steam condenses back into water, shrinks, lowers the pressure in there, and the outside of the barrel still has to stand up, remember, to atmospheric pressure pushing in. Ooh. Yep. That's what happens when you lower the pressure inside. There was no way for air to get in to build the pressure up again. Atmospheric pressure was too much, and bang, it collapsed.
Liquid gas carriers instantly turn steam back to water using flash condensation. And that creates a low pressure area, like my vacuum jar, in which they boil seawater at just 50 degrees C. They don't bother with the marshmallows. That was just my idea. Thanks to a principle noted by the father of evolution, gas tankers save a huge amount of energy. And energy is the precious cargo these ships deliver. This is not some fuel-wasting monster carrying a ticking bomb. This giant ship is a smart and self-sufficient recycling plant. It takes all the water it needs from the ocean. It generates its own electricity, and its own cargo powers it day and night around the globe.
You could say these ships are like huge self-propelled gas bottles. Well, you could. But the fact is they are remarkable vessels using extraordinary technology to keep a potentially hazardous cargo safe and very cold.
And it was all made possible by stainless steel cutlery, a problem with the fire truck, an ancient method for opening tomb doors, Charles Darwin's potatoes, and a pre-war mail plane.
Next here on BBC Two, roads, fields, sewers, it's all fair game for the Top Gear team. And over on BBC Three, now you can catch highlights from the Spanish Grand Prix circuit.